I need your title. We'll talk to us on
It
spectral gaps and conformal bootstrap. I hope you'll define some of the things.
I'll give it a shot. Some of them at least. Yeah. So thanks a lot, Peter. Thanks for inviting me at the occasion of the beautiful lectures that Marina gave. Thanks also to her for those lectures. And yeah, sphere packing, spectral gaps, and the conformal bootstrap is the title and the topic. And so more concretely, broadly speaking, the topic is sort of deriving spectral bounds in various settings from linear programs. These linear programs are typically infinite dimensional. So if you followed Marina's lectures, you saw how this works in the sphere packing case. And today there will be two other mathematical objects that where similar ideas can be applied. So besides sphere packing, there's also hyperbolic manifolds and conformal field theories. Somehow all of the vertices of this triangle will be connected in some pretty interesting way. That's the goal of the talk, to explain how all of this is connected and how you can use linear programs to say something interesting. So the general sort of idea or algorithm for producing spectral bounds in this setting is summarized in these 4 steps. So first you formulate some identities satisfied by the spectral data, and I'll say concretely what the spectral data is in those cases. In the second step, you translate these identities into some linear or semi-definite programs. Then these linear programs lead to bounds on the spectral data. And in favorable circumstances, you can prove, these bounds are provably sharp, as for example happens in 8 and 24 dimensions for the sphere packing. But actually one of the points of the talk today is to exhibit another example where this bound can be proven to be sharp. The plan is the following. In the first half of the talk, I'll talk about some newer work on the spectral gap of hyperbolic 2 orbifolds. And so the talk is a bit not chronological, because in the second part, I'll talk about some older work, which is spectral gap in conformal field theories. And this is the case where we can prove some sharp bounds using a method which is a generalization of Marina's method of the contour integrals of modular forms. So I'll explain all of that. First, the first part, spectral gaps of hyperbolic 2 orbifolds, and this is based on a paper that I wrote with Peter Kravchuk, Sridhar Pal. Sridhar is over there, about 2 years ago. So this is the setting. Gamma, discrete co-compact lattice in PSL2R, gives you a compact hyperbolic 2 orbifold by quotient the upper half plane, a gamma. Then the problem that we are interested in is solving the Laplace equation on this orbifold. So this is the Laplace equation, Laplacian on the upper half plane, and you're solving it in a space of functions invariant under this gamma. And because it's compact, you get a discrete spectrum starting with 0, and then there's a spectral gap lambda 1, lambda 2, and so on. So the main player of the talk is the spectral gap, this first positive eigenvalue. And the summary of the method that we basically introduced is to use some harmonic analysis and representation theory of this group of PSL2R to formulate some linear programs which produce upper bounds on lambda 1 for a given topological type. So topological type is, just the genus. If it's a smooth manifold, but more generally, when it's an orbifold, the topological type also includes information about the orders of elliptic points. So for a given topological type, you can prove an upper bound on lambda 1, and very often this upper bound is nearly sharp, and possibly exactly sharp, but not quite sure yet. So first some results before I actually tell you what the method is in detail. The first part of our results is an upper bound on lambda 1 of fixed genus, this theorem that we proved in this paper, but also it was proven by James Bonifacio independently. The genus 2 showed that every hyperbolic orbifold satisfies this upper bound on lambda 1. So you can interpret this, this should be interpreted as an exact rational number. And actually this upper bound is nearly saturated by a Boza surface, which is a very symmetric point in the genus 2 moduli space. There's some 6-dimensional moduli space, and upper bound applies everywhere, but there's a special point where it's nearly saturated. And at genus 3, something similar happens, where our upper bound is this 2.678 and so on. And in that case, there is a much bigger moduli, like this 12-dimensional moduli space, and a special point in it, the Klein quartic, nearly saturated. So this is an example of a setup where you have linear programming bounds that are nearly or exactly saturated. And Another question that we asked in the paper is, what is the image of the map that takes an orbifold to its first eigenvalue when X ranges over all of the orbifolds? So what is the sort of spectrum of lambda ones attained by all orbifolds? And we gave this answer, which is almost proven, besides some small point that I'll discuss later. And the answer takes the following form. So this is the set of lambda ones appearing in all orbifolds. There is a closed interval starting at 0, going to the 15.79. Okay, here these quantities above the real axis, they denote the topological type. So first entry is the genus. It should be a semicolon. So this is genus 0, orbifold points of degrees k1 up to kr. So this is 2, 2, 2, 3, meaning a sphere with 4 punctures of degrees 2, 2, 2, and 3. And then there are 3 isolated points. I should say this interval is spanned by the moduli space of the 2, 2, 2, 3. And there are 3 isolated points corresponding to triangles of these degrees, 2, 3, 8, 2, 4, 5, and 2, 3, 7. The triangles have no moduli. Sphere with 3 punctures have no moduli. So I'll discuss how to prove that in maybe 10 minutes or so. The summary of the method is the following. It's quite similar to the method that Bernstein and Reznikov used to prove some bounds on triple products. And it goes as follows. First, we implement the topological type by looking at the spectrum of the holomorphic discrete series in this Hilbert space. So there's the Hilbert space of L2 functions on the G mod gamma. And holomorphic discrete series corresponds to holomorphic modular forms on the orbifold. Then we consider these integrals of quadruple products where f bar and f bar belong to these holomorphic discrete series representations. Then you do spectral decomposition in 2 different ways. The product of f and f expands holomorphically, and f bar expands using the principal series, which is the Laplace eigenfunctions. And by comparing these 2 different expansions of this integral, we get infinitely many spectral identities of the following form. On one side, you're summing over the Laplace eigenvalues. On the other side, you're summing over the holomorphic forms. And well, in principle, if you knew all of this holomorphic data, you could compute the lambdas to any precision. But that's not really our goal. Our goal is just to use this to set up some linear programs in the space of these identities to get optimized upper bounds of lambda 1. And here's maybe a more clear representation of it. The Hilbert space decomposes into these irreducible representations, constant, trivial representation, discrete sum over the principal series, discrete sum, so this is the Laplace eigenfunctions, this is the holomorphic modular forms for the discrete holomorphic and anti-holomorphic, and are the weights of the modular forms that appear, which are fixed by the Riemann-Roch theorem. And then we consider this integral of a quadruple product, f bar, expanded in 2 different ways. So either we fuse sort of f2 with f3, that gives us sum over the Laplace eigenfunctions, or we fuse the f with f, gives us sum over modular forms, so they have to be equal to each other because this is just a well-defined single number. And a crucial point is that the contribution of a fixed irreducible representation, of a particular irreducible representation, is completely fixed by representation theory. And that's due to this special property of the group BSL2R, which is that uniqueness of trilinear functionals on products of representations. So when basically the space of trilinear functionals on D times D bar times P, or D times D bar, is just 1-dimensional for this group. So that means that each of these terms is basically just fixed by gluing these 2 trilinear functionals to each other.
Are they compact orbifolds?
Yeah, well, this is okay. Well, the same idea applies also to non-compact ones. I mean, but then you have some continuous spectrum, like the Eisenstein series, and the Eisenstein series is going to contribute here on the left-hand side. Okay, so the only thing you need to, is it what you're asking? Or how?
I'm asking if you're talking about compact or non-compact orbifolds.
I'll only say interesting concrete things about compact ones, but at this point, this still applies generally. So for non-compact ones, you just have you would also have a integral over the Eisenstein series here on the left-hand side.
But his lambda 1 is the smallest non-zero eigenvalue, so it would always be, you would already get stuck at a quarter.
A quarter. All of these upper bounds that we get, they're always above a quarter, so we haven't learned anything new about lambda 1 of.
I'm going to ask if you could pick up the Cospedal.
I don't think so.
If you could
ask on a non-compact orbifold, you can ask about the spindle part of
yes
too, and if you could just restrict to this and then say something.
Yeah. No, exactly. I don't know how to do it. If you could somehow get rid of if you could maybe exactly compute the contribution with Eisenstein, probably you can't do that, but if you could somehow get rid of the Eisenstein series on the left-hand side, then that's how you would do it. Yeah. Here, maybe in a bit more detail, what these spectral entities are. So proposition. Let's suppose that our orbifold admits a holomorphic modular form H of weight 2n. So n is the label of discrete series. The convention is that the weight of the modular form is twice that. And let phi j be the complete set of Laplace eigenfunctions and denote this overlap between h. So h is a modular form. This is just the contribution of phi j to the product of h and h bar, Peterson inner product, and let this be the norm of the mth ranking Cohen bracket. So this is ranking Cohen bracket of degree m, some holomorphic modular form of weight 4n plus 2m, and this is just its Weil-Peterson norm. Okay, then the proposition says that there is an infinite set of spectral identities parameterized by a holomorphic variable z. So this is true for any z in the complex plane, basically without this interval. And on one side you have an infinite sum over the holomorphic modular forms of these ranking Cohen brackets, norm squared, times some special function. On the other side, you have this other positive quantity, which is the inner product squared, times some other special function. And what are these special functions? Well, there are some Gauss hypergeometric functions, 2f1. The holomorphic discrete series looks like this, the contribution, for weight m and geometric parameter z. And on the other side, looks like some other Gauss hypergeometric 2f1. So 2 comments, the z parameterizes the different vectors that we could have chosen here. Here, for each f1, f2, f3, f4, we can choose out of infinitely many vectors in these representations. And this can be packaged into choosing this value of z. So it can be parameterized by a single complex number. And these h and h twiddle, you can compute them as solutions of a second order differential equation. So this arises. So there is a quadratic Casimir for this universal enveloping algebra of SL2R, and it acts like a constant on irreducible representation. So the contribution of a fixed irreducible representation to the sum needs to be an eigenfunction of the second order differential equation. So that's how you can actually how you can fix it. And by the way, it's just the Legendre. Ultimately, it's just the Legendre differential equation. So these are some other solutions of the Legendre differential equation, which actually have logarithmic singularities. Maybe this is the most important part so far. So if there are any questions about it, about anything that I said before, feel free to ask. But okay, the picture is that there are some spectral identities relating the holomorphic data to the mask to the Laplace eigenvalues. Or the spectral parameters appear as parameters of the hypergeometrics.
And you're just going to use the fact that it holds for all z,
yeah, I'm gonna use the fact that it holds for. I'm actually just going to expand it at small z, and I'm going to use the positivity of these coefficients. That's the most important part. That these coefficients are positive for some norms. Okay, so something that you can actually do here is that you can solve for the ranking for these norms. So we can just kind of invert this equation for these coefficients, and in this way you can write the coefficient as an infinite sum over the Laplacian spectrum of these positive numbers times some polynomials in lambda. So these are polynomials which are just fixed by representation theory of PSL2R. Here's a formula for them. There's some explicit polynomials that you can compute. Another piece of data is that the ranking Cohen bracket actually vanishes for odd m because of symmetry reasons. So for example, for m equals 1, you just get this identity that the sum over Laplacian spectrum of these positive numbers times lambda minus n vanishes. So this kind of tells you there have to be some small eigenvalues for which this is negative and some large eigenvalues for which this is positive. So it's starting to tell you something about distribution of the eigenvalues in some rather non-trivial way. Okay, but this doesn't really teach you anything about the spectral gap because there's an identity which is already negative. But you can go one step further, take linear combination of the first and third spectral identity, and you get this kind of identity. So it's a sum of these positive numbers times a cubic polynomial. Okay, this cubic polynomial is easy to fix using this rep theory arguments. And you can plot this polynomial, and you see it has some negative region shown here and some positive regions everywhere else. So this gives you, crucially, it vanishes at the identity. So identity doesn't, the trivial representation doesn't contribute here. So there has to be at least one eigenvalue here in this red region. So it gives you an upper bound on lambda 1, which is just this root, the upper root of this polynomial. Depends on n. Okay. You can do all of this pretty much by hand. And now you can compare this upper bound with some experimental data. So it's this comparison to experimental data. You can compare it for the different eigenvalues for various values of n. So let's take this to be the minimal weight of a modular form on gamma. And there are just 5 possibilities for n as well.
This is a key input, right? You're going to throw away gamma and just input this. Yeah.
So the only thing that we are keeping about gamma is that it supports a modular form of weight 2n. And if we take this to be the minimal one, then there are just 5 possibilities: 1, 2, 3, 4, and 6 for the value of n. And for each of them, you can write what this upper bound is and compare it with the largest known lambda 1 for an orbifold that supports a modular form of that weight. And you can see that for each of these values of n, even this sort of very simple to derive bound gets pretty close to the actual largest known lambda 1. So for example, for n equals 1, there's a torus with a degree 2 elliptic point, special point in the moduli space of this one, has a eigenvalue of 8.47. It's quite close to this 8.61. And basically for all of them, maybe except for n equal to 4, they are all within 0.1, 0.2. But you don't have to stop there. You can go once.
You should also probably say that largest, I mean, when you're computing that, you're computing it another way for those gammas.
You mean the largest, this column, or?
Yeah.
Well, this column I think we were just computing it using some finite element method.
Oh, okay. All right.
You could compute it using the trace formula if you wanted to.
Yeah, I'm just saying it's a different way.
Yeah,
Actually computing it.
That's right. Yeah,
it's quite intensive. Yeah.
Yeah, this is pretty hard, but this is you just evaluate this fraction. Yeah. Okay, so this just comes from two of these infinite limit identities, right? Now you can use all of them and systematize it using linear programming. So that's this proposition. So let's m is the dimension of the truncation of the linear program from infinity to m, and let's take some linear combination of these polynomials, which is parameterized by some coefficients x. And now there are some constraints on these coefficients x, which ensure that we get a bound. So the first one is that these coefficients are non-positive for even m. There's a normalization at identity, and then there is a positivity above lambda star, which is the gap that we want to prove. So if you can find the values of x such that this linear combination satisfies these properties, then if you have an hyperbolic orbifold that actually supports a homomorphic form of weight 2n, then you get an upper bound on the Laplacian spectral gap, which is this lambda star. And that's just a systematization of the procedure from the previous slide. You consider this infinite sum. You exchange the sum over J with the sum that defines Q. You evaluate it using the identities, and then you use sort of this non-negativity to find that this sum has to be non-positive. So at least one term in this sum has to be non-positive, or at least one term in this sum has to be negative. And therefore, from this property 3, you get an upper bound on the spectral gap. So that's linear program. And okay, in practice, we minimize the value of lambda star by optimizing over these axes, and eventually increase m to approximate the infinite dimensional program as well as we can to improve the bound. And to do that, we use this semi-different programming solver that David Simons-Duffin developed in the context of the Conformal Bootstrap that I'll get to in a second.
Is it clear that as you let m go to infinity, you're going to get the sharp answer?
No, it's not clear. Actually, it looks like you're not really getting a sharp answer in this case. Unfortunately, it's okay. I'll discuss it maybe in a few slides. And here are the results for the different values of n. 1, 2, 3, 4, 6. This is the linear programming upper bound on lambda 1. And this is the value of lambda 1 that you can compute using your favorite method for computing the spectrum for the orbifold that we believe maximize the lambda 1 in that particular class. And for example, for n equal to 6, see the agreement is quite good. It's to 5 decimal places. This upper bound that only uses the fact that there is a weight 12 modular form agrees with the lambda 1 for the 2, 3, 7 triangle. Something deep seems to be going on maybe. And yeah, you can ask this question that Tom asked, what about, are these bounds sharp? So is this linear programming upper bound on lambda 1 sharp when m goes to infinity? Actually, if this is true, then the linear program needs to be able to reconstruct not just lambda 1, but the full Laplacian spectrum. This is kind of because if the bound is sharp, then all of the inequalities, all of these inequalities have to become equalities. And that means that this Q has to vanish on the entire spectrum, and because it's non-negative, it has to vanish to some even order. So this Q should have double zeros probably at all of the eigenvalues of that surface. And you can compare this expectation with the actual output of the linear program. So this is the plot of the output of the linear program that only assumes that we have a modular form of weight 12, nothing else. And there is a first order zero, a second, and a bunch of second order zeros. And all of them are very close to actual eigenvalues of this surface, of this 2, 3, 7 triangle surface. That's quite striking. That even just using the information that there is a weight 12 modular form and setting up this kind of rep theory harmonic constant linear program, you recover a very good estimate for the first, say, 5 eigenvalues of a particular surface. Upper bounds on lambda 1 for orbifolds of fixed genus. So this is something I advertised before already. Here we are just going to use the fact that for genus G, there's a G-dimensional vector space of weight 2 holomorphic modular forms, and consider the system of quadruple products with where each of these H's ranges over a basis of these modular forms. But again, we are not really using explicit formulas for these modular forms. We are just using the fact that there are G of them, nothing else. And then you have these results at genus 1, 2, and 3. Our upper bound is shown here. So 8.47, we already saw that. At genus 2, it's 3.8389, quite close to the Boza surface. And at genus 3, 2.678, quite close to the Klein quartic.
As a matter of curiosity, do these finite element methods give you upper bounds or not?
I don't know what they give actually.
I think if you use the trace formula, you can actually be confident.
The trace formula, you can be reversed. You can get both upper and lower bounds
to any accuracy by computing more and more terms in the trace formula. So I think you can assume they're correct.
Yeah, I think these numbers should be correct to all the decimal places that we show. And again, so the only fact that we are using here to get these upper bounds is that there are G linearly independent n equals 1 modular forms.
Yeah.
Okay, then finally, about how we find a set of lambda bounds which is attained by all orbifolds. So we can basically get some more refined upper bounds on lambda 1 by using not just the lightest modular form, but say the first 2 smallest n modular forms. So with weights 2 and 1 and 2 and 2, and then consider this system of spectral identities coming from these quadruple products, H, I, J, HKL, where I, J, KL range over these 2 different modular forms. So now you need to be a bit careful because you can. I think it's still true that you have this uniqueness of triple products, and the correct representation that you expect appear. The method generalizes pretty straightforwardly. You just need to modify a little bit the form of these special functions. They still solve some second order differential equations, so it's all good. And one example of a bound is, let's say you assume that you have a surface that has n1 equal to 6 and n2 equal to 8. Then this linear program from this setup gives you an upper bound, which is 23.0997. which is nice because this number is less than 44. So then how do we use this to produce this picture for the set of lambda ones? So basically the first step that you want, well, the zeroth step is that we already know that there is nothing to the right of about 44.888 because we already proved that there is an upper bound for 1, 2, 3, 4, and 6 for a single modular form. So there's nothing to the right. So now we need to say prove that this 237 point is isolated. So we just need to prove an upper bound on everything which is not 237. And the way to do it is that you can split all orbifolds into 3 classes. And the first class is just the 237 surface. It's the only one that has n1 equal to 6 and 2 equal to 12. In the second class, if it doesn't have n2 equal to 12 but has n1 equal to 6, then it has to have n2 equal to 8. Actually, that's quite easy to check using the Riemann-Roch formula. In that case, this example applies. So you get an upper bound of 23. And everything else has to have n1 less than or equal to 4. And then we already know from before a bound which is better. It's 30.3543. So now this means that there is, to the right of 30.35, the only thing that can appear is this 237. And in this way, you can kind of systematize it and keep going until you reach this continuum, at which point you still need to prove something. And that's something we haven't proved. It would be nice to prove it. So if you have some ideas, please talk to me. So we need to prove that the top of the continuum of this moduli space of the 2, 2, 2, 3 occurs at a specific point, which is the one where this 4-punctured sphere covers this 3-punctured sphere, 2, 2, 3, 9. So it's a point where
you prove it's local maximum.
I haven't proved that it's a local maximum, but maybe it's not too hard because this moduli space is just 2-dimensional.
Too real.
Too real dimensional, yeah.
I think once you prove it's a local, then you're done for sure. Then it's just a brute force. And the local should come from symmetry. Yeah, we should discuss this some more.
So you have some idea about how the eigenvalue moves when you, Peter?
Let's talk about that after.
Okay. So this is the picture. So basically the conclusion is that this approach of linear programming with representation theory is quite powerful for determining the spectra or upper bounds on the spectral gaps, and actually gives you a lot of information about also distribution of the eigenvalues, which I haven't really discussed. But these identities seem to constrain the eigenvalues in a rather powerful way. There also have been some additional developments in this direction. So first there was a paper by Fortier-Bourque and Patry this year, who applied linear programming not to this associativity, but to the Zilbert trace formula, and they got some pretty nice upper bounds actually at higher genus. So I didn't show you our bounds at genus more than 3 because they are not so good, but their bounds at genus greater than 3 are better than ours actually, and they are.
Genus 6 or more.
Genus 6 or more, yeah.
Landscape.
Then later this year with Sridip and with James Bonifacio, we apply the same idea to hyperbolic 3 manifolds. So their representation theory is a bit more complicated, but you still have this basically this uniqueness of the triple product, or this finite dimensionality of the triple product. So it all works very nicely. And we proved some upper bounds on the spectral gap for, say, all hyperbolic 3 manifolds with a positive first beta number. And finally, Sridip and his collaborators are putting out a paper soon about how these ideas apply to spin basically Laplacian on spinners, or the square of the Dirac operator. And there, you can repeat many of the things we did, and there are some more cool results about the spectral gaps. So that's the end of the first part of the talk. Maybe if you have any more questions about it, now is a good time to ask.
So the thing about spinners, it's like producing spectral gap on spinners, or it's taking in the existence of harmonic spinners?
He's the person to answer.
Yeah, so you can use the fact that, for example, in the hyperelliptic part, of the moduli. It can have maximum number of spinors.
Okay.
And you can use that information to put a bound on the Laplacian on the hyperelliptic part. So that's one thing I can do. And another thing you can do is put a bound on the spinor gap conditioned on the scalar gap.
Okay, so now the second part of the talk is about some auto work, which is how these things are related to sphere packing and to conformal field theory. This is based mostly on these 4 papers. Yeah, so the overview is as follows. So I'm going to discuss a linear program, which is quite similar, but not exactly the same as the Cohn+Elkies linear program in D dimensions. But the nice thing about this other linear program that I'll describe is that unlike the Cohn+Elkies one, it actually admits an analytic solution for any value of the D. So in the Cohn+Elkies, you can only solve for 8 and 24 dimensions, but this other one, you can solve for any D. And actually, this linear program and its solution were discussed and discovered in some mathematical literature on conformal field theory and for the conformal bootstrap. So this is the field that I come from, and I'll tell you what conformal bootstrap is. And this is how I got into all of this business of linear programming and sharp bounds and so on. And for 8 and 24 dimensions, there is actually a precise mapping between the solution that was discovered in the context of conformal field theory and this Fourier-Odd magic function for sphere packing. You could sort of go in between them, and this solution from conformal bootstrap generalizes this magic function to any value of the dimension. And also this basis of interpolation functions that played an important role for universal optimality also makes a natural appearance in the conformal bootstrap problem. Yeah, just to set the stage, let me review the Cohn+Elkies bound. The Fourier-Odd Cohn+Elkies is bound on the spectral gap of isodual lattices. So isodual lattice is a lattice whose dual is just isometry applied to itself, to the lattice. And then you can define the spectral gap S1 to be the shortest, the minimum of the norm squared of non-zero lattice vectors. So the shortest non-zero lattice vector squared. And this is important because it controls the sphere packing density. The largest sphere you can put into this lattice is one whose radius is 1/2 of the shortest lattice vector. So this is the density. The volume of the unit cell is 1 because of its isodual. And then more general, let's define the spectrum to be just the set of norm square of all lattice vectors. So it starts at 0 for the 0 vector, then S1 is the shortest one, S2, and so on. For example, the E8 lattice would have all even integers, and the Leech lattice would have all even integers except for 2 in the spectrum. Now, the spectral identities that play the role for the hyperbolic manifolds, now they are just the Poisson summation formula. And we can restrict to Fourier-Odd radial Schwartz functions because the lattice is isodual. And the Poisson summation formula is just that the sum over the lattice vectors of fx over fx is equal to 0. Cohn+Elkies bound. Cohn+Elkies taught us how to prove upper bounds on the spectral gap using this linear program. So you want to make f0 to be positive and f to be non-negative above some value R1. So if you can find such a Fourier-Odd f, then you find an upper bound on the spectral gap of all isodual lattices to be R1 squared. And the proof is just you apply 1 and 2 to this Poisson summation formula. There has to be at least one negative term. So you find an upper bound.
I mean, as Marina explained, it also gives a bound on sphere packing, not just lattice packing.
Maybe not this one. Because here it's Fourier-Odd radial Schwartz.
Yeah. I'm just
at the odd part, yeah.
The odd one is just but somehow in practice the even one just kind of goes along for the ride. That if you can find in practice what Cohn+Elkies, I guess it's not really proven, right? That if you can always for any D you can find the even one if you can find the odd one. But this is
far from it.
Yeah.
It might not even be true.
So it may not be true. Well, it's.
I don't have counter example, but yes.
But I want to focus on the Fourier-Odd part because it captures all the essence of the problem. But you can generalize this to the full sphere packing. I mean, the magic function already makes sense just for this Fourier-Odd part. Okay, and then the remarkable thing that, of course, we know happens is that the optimal solution of this linear program reproduces the spectra of the optimal lattices. So in 8 dimension is the E8 lattice, whose spectrum is all positive even integers, and for 24 dimension it's the Leech lattice, the positive integers except for 2. So this is something quite remarkable. And there's a useful point of view, which I think Marina also discussed in her lectures, is this applying the Poisson summation formula to the Gaussian. So Gaussians sort of form a complete set of Schwartz function, radial Schwartz functions. So here's the Gaussian, e to the I pi tau s. S, remember, is the spectrum, so it's like x squared. And I want to normalize it by this d power of the Dirichlet eta function. And the reason to do that is that then this Gaussian satisfies nice end. So if you take a Fourier transform of the Gaussian, then you get back the Gaussian with tau replaced by -1 over tau. So this is the key identity that the Gaussians satisfy, which means that the Poisson summation formula in the basis of these Gaussians for various values of tau just becomes the spectral identity. It's sum over the lattice, gx squared tau, and this sum on the left has to be invariant under tau goes to -1 over tau, everywhere in the upper half plane. So which question does the Cohn+Elkies bound answer sharply in general D? Well, it's this question, this nonlinear optimization question of trying to maximize the spectral gap such that there is some spectrum and positive coefficients such that this sum over the Gaussians is invariant under tau goes to -1 over tau. So if you now that was Cohn+Elkies, now the conformal bootstrap. So the conformal bootstrap is about trying to constrain conformal field theories, but we don't really know the conformal field. We don't really know how to construct conformal field theories. So usually we just write down some axioms, conformal invariance and so on, and try to prove some spectral bounds starting from these axioms. Here's a kind of a simplest case of that idea. So the conformal field theory would be, first of all, some unit representation of this universal cover of SL2R, which composes discretely as a sum over lowest weight representations of this SL2R universal cover. So these are like a discrete series from before, but their spectral parameters can be any real numbers. They don't have to be, for SL2R, they don't have to be integers, but for the universal cover, they can be any real number. And besides that, there is a product structure, which is something like a multiplicative abelian structure on this Hilbert space. It seems to be compatible with the action of SL2R. And this is called the operator product expansion. And I don't want to go into too much detail, like what are the subtleties here, but I'll just say what it means in practice. And the point is that just like for hyperbolic orbifolds, the spectrum of these S's is tightly constrained by associativity of this product. So the task that we were thinking hard about in the context of conformal field theory is, suppose that there's some dp appearing here, so p is in the spectrum, and then we want to prove an upper bound on the spectral gap with a small print that is just a spectral gap in the subspace of V generated by the product of dp and dp. So even when p is very small, if this upper bound is kind of larger, it's still interesting because this upper bound doesn't necessarily apply to the p itself. But just
is there another algebra, the Viazovska algebra or something like that, that's in the background? Yeah.
Here there's no Viazovska algebra. It's just harmonic analysis on SL2R.
But in the that's in this example.
Yeah, in this. Well, this is somehow the simplest example where things make sense, and this is the example that gives rise to a linear program that can be solved analytically. Once you have a Viazovska algebra, you can no longer do it. So the Viazovska algebra just kind of complicates things, and it's not essential for it. It's not a part of the essence of the problem.
So what does spectral gap mean? Can you explain spectral gap in terms of the unitary dual of I guess SL2 tilde is the universal cover, right?
No, the unitary of the universal cover is just that all of these numbers are non-negative, or no. But
no, what does spectral gap mean? Like for SL2R, are you talking about complementary series representations? Here, what does spectral gap mean? So
I'm defining some object, which is unitary representation together with some product structure, and it turns out that if you make S1 too large, then such a thing cannot exist. It is not compatible with this product structure.
Right. What does spectrum S1 mean?
What is what, sorry?
I'm asking what does S1 do?
S1 is the
Oh, okay.
the smallest positive as that appears in this direct sum.
Oh, so it's just about, but this is weird. So these are all discrete series? These are like,
There are discrete series for this SO, right, the cover of the SO2R. So
with arbitrary weight guards. So it's
Arbitrary.
like a multiplier system, which is it's non-linear, the group now. Yeah.
okay, that clarifies things. So it's the weight of the generalized like discrete series.
Yeah, it's the smallest weight here. That S0 is just one-dimensional representation, and all of the rest is infinite dimensional. And the question is, what is the first infinite dimensional one that appears? And it turns out you cannot make it arbitrarily large. If you make it arbitrarily large, then you cannot satisfy associativity. It's very similar to what happens for the hyperbolic surfaces. But this is somehow even simpler because, okay, so what was the equation? Now the associativity is kind of symmetric. This is the analog of Fourier odd, that you got the same kind of sum on the two sides. Now the special function is the same special function that we saw for hyperbolic surfaces. Just the S becomes a continuous parameter. And now the sum is, okay, there's some sum over the spectrum with positive numbers, which is invariant under Z goes to 1 minus Z. So the Z goes to 1 minus Z implements this different change of channels, the different ways of expanding it as before. So Z parameterizes the different vectors. And for each value of Z, this is in some open set, this is a true identity that follows from the associative product. Okay, so here's the comparison between that problem and the Cohn+Elkies. So the task basically is to now maximize the spectral gap such that there is some spectrum, some discrete spectrum starting at 0 with some spectral gap, and such that there are some positive coefficients, such that when you form this sum of these special functions, this is the special function, then it's invariant under Z goes to 1 minus Z on one side. And for the Cohn+Elkies, it's just the same story, except you have different special function. You have the Gaussians instead of these two F1s. So in both cases, some Gaussians, hypergeometry is the Gaussian. And it's invariant on minus 1 over tau. Okay, and then you can, what is this maximal S1? And actually the answer is known in these cases. So in the conformal bootstrap, this is the answer for general positive value of P. And so it's 2P plus 1, the maximal spectral gap. And this was proven first for all half integer, for n over 2, all half integers are integers. And then eventually it was also proven for n a positive P. And the extremal spectrum is just an arithmetic sequence. So it's basically the all even integers shifted by 2P minus 1.
This is in the context of the representation theory simply of SL2 tilde, right?
Yeah.
There's no any unitary representation.
Yeah. There's no Brassard here.
And there's no gamma.
There's no gamma. And on the other side, Marina famously proved the maximal spectral gap being 2 for 8 dimensions, and with Cohn, Kumar, Miller, and Radchenko, she proved that for 24 dimensions, this maximal spectral gap is 4 for the Cohn+Elkies linear program. Okay, so there are some similarities, and actually it's, for a while we just thought there was some analogy between these two problems, but then eventually we proved it's much more than just an analogy. It's really a very precise mapping. So that's what we explain here, that you can go in between the two problems using the modular lambda. So if you substitute Z being lambda of tau, and if you map the parameters, so this P being the weight of the modular form P being the weight of this discrete series, it's equal to D over 16. So the Cohn+Elkies in D dimensions is related, can be mapped to, it's closely related to this conformal bootstrap where P is D over 16. And in particular, the Fourier odd magic function can be recovered from this proof for P equals 1/2. So P equals 1/2 gives you 8 dimensions. P equals 3/2 gives you 24 dimensions. So yeah, you can use this to go one way, or you can also go the other way. So you can, if I had known about Marina's work, I could have proved this theorem for P equals 1/2. Like my paper was later than Marina's paper on the same year. I didn't know her about her work, but this magic function generalizes it to any positive P. So okay, in the rest of the talk, I'll explain how we did it, and what was our way of thinking. First, this is still a bit not chronological, so eventually I'll tell you how we did it before we knew about the mapping to sphere packing, but I think I want to say a little bit more about the mapping to sphere packing. So the key is this modular lambda function, which maps the fundamental domain of gamma 2 to this cut plane. So it relays the tau to z. And the key is that the S transformation, when it acts on tau, goes to -1/tau, it just acts on z as z goes to 1 minus z. So that's the two sides of the equation, right? The two sides differ by the S transformation. Z goes to 1 minus z, or tau goes to 1.
This slide for me.
Oh, sorry, this slide? Yeah.
The S1 maxes on the two sides are the same.
Hmm?
In the two theorems, S1 max.
Yeah.
Same?
Yeah, for P, sorry, for P equals 1/2, so the eight-dimensional sphere packing is a special case of this when P is equal to 1/2. And
why are there not more theorems? Like P is 1/2, P is 3/2, P is 5/2.
Oh, because I'll explain. They're not the same. These two problems are not the same. They're closely related, but that's what I was about to explain.
Okay.
Okay, so there is the S transformation, which maps tau to -1/tau, and then there's the T transformation, which maps z to 0/z-1. And as I already said, these spectralities express some invariance of the spectral sum under the S transformation. So this is the conformal bootstrap with dp. This is the Cohn+Elkies with an RD. Okay, so you see the two sides are just related by the S transformation, but for different special functions. Okay, now what about this relation? Why is the d-dimensional Cohn+Elkies related to this dp? Of course, d equals 16p. Well, if these functions were actually the same function, then they would be exactly equivalent, and I wouldn't be telling you anything new, right? If this hypergeometry, if it were true that you act with the module lambda, you just get the Gaussian, you would get an exact equivalence, but that's not true. So that's why the problems are not the same.
You get new theorems, right?
Hmm?
You get new theorems from P is 5/2 and
well, you get new theorems, but not about the Cohn+Elkies. Can I first explain it?
It's explaining it.
I'm explaining it. I'll explain everything. Okay, so they're not the same. They're not the same function, but they are both eigenfunctions of the t with the same eigenvalue. So this is kind of the key point. There is S and T, and that's all you need to know. That under S you just go from one side to the other, and under T you get it's an eigenvector with the same eigenvalue. So this H under T gets e to the I pi s minus 2 to 3 over p, and the Gaussian just pick up this other phase. And if you compare them, you see that d has to be equal to 16p.
And sorry, what is the action of t here? Okay, just action
on the Gaussian. So you get a phase from here, and you get a phase from the Dedekind eta, which is s minus d over 24. And here z goes to 0/z-1. It's a symmetry of the differential equation. So this is just the monodromy of the differential equation. Okay, so a few more.
Just go back. So there's unequal. Something is not equal. Yeah.
So this solution of this differential equation is not the same as the Gaussian, but it's almost as good in some sense, because it's for the same magic function to work, you only need them to be eigenvectors of t with the same eigenvalue. But it will become more clear hopefully as I go on. So okay, so here's a statement. So actually a bit more is true. So you can take the Gaussian in d dimensions and expand it using the hypergeometrics with positive coefficients. And the hypergeometrics that appear have the same spectral parameter plus even integers. Okay, so this is, if there was just the first term, if the g equals 0 was just here, then there would be the same problem, but they're not the same problem because you get this whole infinite sum. But the infinite sum has a lot of structure because they are shifted by even integers. So that means that you can solve both problems using the same method, but you can only solve using the same method for those values of p where the extremal spectrum kind of overlaps with these shifts. So when the extremal spectrum for the conformal bootstrap is 2p plus 2j minus 1, and you can only this is only compatible with these shifts when p is basically 1/2. So this gives you a spectrum being 2j. Okay, so this is why I said this happens only for 1/2, which is 8 dimensions, or for 3/2. For 3/2, it's 24 dimensions. There's some small discrepancy that's equal to 2, but it can be fixed by a small adjustment, which is just adding a constant to this modulo j. And for the other values of p, the solutions of the two problems on that slide are not the same, are just not the same problem. Okay, so that's somehow the
What happened to 2?
What is 2?
Dimension 2, where
In dimension 2 is also, yeah, you see, when the dimension 2 is p is 2 over, so it's 1 over, there's a shift of a quarter here, so it's, yeah, there.
it doesn't match because that
It doesn't
match. And that is a case where I believe the linear program.
Yeah, it does, but it doesn't work because the spectrum is not a part of a perfect arithmetic sequence including 0. That's only true in 8 and 24 dimensions. I mean, the spectrum is just more complicated in 2 dimensions. So this bootstrap doesn't seem to help you to solve the 2 dimensions here. Okay. So now let me say how we proved the optimality of this bound for general P. So how we proved that for the conformal bootstrap, this is the optimal bound. There is an easy part, which is the existence. So first, that the bound cannot be better than 2p plus 1. So this is the unlock of exhibiting the E8 lattice and the Leech lattice, that the bound cannot be better and can rule them out. So let's say that the spectrum is P admissible if you can find a positive coefficient such that this spectral sum is invariant and is equals to 1 minus z. And well, there's a small lemma, which is that the spectrum which I claimed was extremal is actually P admissible. So this is that this arithmetic spectrum works for any P, and the way you prove it is that you write down this function, which is the 4-point correlation function of the free fermion in conformal field theory. You can just expand it into these Gauss hypergeometrics with positive coefficients and with this right spectrum, right? So this is the unlock of the theta function of the E8 and the Leech lattice, and there's a closed formula for the CJs, and they are positive. Okay, so this proves this part. And you can compare this free fermion with the E8 lattice and the Leech lattice theta functions, and you find that they are indeed the same. So this is the, if you plug in p equal to 1/2, you get this answer, which agrees with the theta function of E8 lattice, and for 3/2, you get this answer, which agrees with the theta function of the Leech lattice up to a constant. And there's some prefactor which I suppressed from the discussion, but this can be easily. I can explain these prefactors if you want. Okay, but the point is that this kind of generalizes these theta functions to any values of p, and gives you the extremal answer to the conformal bootstrap problem. So we don't have the analog of that for Cohn+Elkies. Like there is no closed formula, except maybe for 2 dimensions for what the optimal theta function should be in that case. Okay, so that's the easy part, and the hard part is proving this upper bound, so that bound is actually sharp. This 2p plus 1. So that and therefore that this theta function, this kind of correlation function, is the extremal solution of the conformal bootstrap for all values of p. Okay. So first, the extremal functionals. This is just a rewriting of the spectral identities. For any values of z, it works anywhere in this plane. Okay, and now we want to act with linear functions. So we want to sort of find the optimal direction in the space of these identities. So we want to construct some continuous linear function omega on a space of holomorphic functions, which satisfy some positivity properties. So let's denote omega s to be how this omega acts on the difference between the h and the s transform of h. Is this notation clear? This is the unlock of the Fourier odd function. Now it's odd kind of under this switch between this part and this part. And there are some positivity properties. On omega is positive at the origin and non-negative above the gap. And then you get an upper bound. So if you can find such a linear function on omega, then you get an upper bound on the spectral gap being S star. And to prove the optimal bound, okay, we use the fact that we think we know what the optimal spectrum is. Right? We want to construct a functional that has double zeros on this arithmetic sequence, except for the first point, where it should have a simple 0. Okay, so this was kind of the information that I was using when I started constructing this functional. Just try to find linear functional, which when it acts on these special functions, it has this structure of double zeros. And if it exists, we usually call it extremal functional. And it plays the same role as the magic function for sphere packing. It kind of looks like this. Okay, and yeah, just like so, how do you get the magic functions from the functionals? So if you do have this function, this kind of functional that satisfies double zeros, then you can get a magic function out of it by acting on the Gaussians, right? So you can just take the same linear functional, but instead of acting on these Gauss hypergeometrics, you act on the Gaussians, and you would recover the correct magic function, because now this is Fourier odd by construction, and it also has the right positivity. So this is the first part. It has Fourier odd, but also has the right positivity properties because the Gaussian expands with positive coefficients. So basically, if you can solve the conformal bootstrap problem, you could also apply it to the magic function, to the sphere packing. So how did I construct this extremal functional? First in the special case, p equals 1/2, which reproduces the 8-dimensional case. Okay, so you want to build a functional which has double zeros, and first let's build one that has simple zeros at the right locations. So this is some general ansatz that I was using. Basically, write a functional that is an integral of a discontinuity on this branch cut. You can kind of convince yourself this is the most general thing that can happen, because for any, say, expanding derivatives, you can pull the contour to the branch cut, and this is really the most general thing that can happen. And this gives you simple zeros almost by construction. On the first, there are kind of two parts. There is the h and the h of z and h1 minus z. So you get simple zeros because of discontinuity of this 2f1, and you get simple zeros here because of symmetry. So there's a symmetry of the Casimir differential equation. So as long as, so I should have said this ansatz is parameterized by some kernel g. Okay, so the goal is to fix this kernel, is to find what is the kernel of this integral. And the claim is that if this g is symmetric, then simple zeros are guaranteed. Okay, and simple zeros on this extremal spectrum. And we now need to impose double zeros. So double zeros will fix this g uniquely. That's kind of the nice thing that happens. Okay, so how do we fix this kernel? So something that I proved, or at least that I explain in my paper. Maybe it's not completely rigorous, but at least I exhibited these functions. So if there is a basis, claim that there is a basis of functions which looks like some kind of slightly complicated linear combination of these two f1s. Like all of them are solutions of the same differential equation, but they're kind of transformed. They're mapped to each other by this S3 group, which is the quotient of SL2Z by gamma 2, generated by SMT. And these functions form an orthogonal basis for the symmetric subspace of this function on this interval. And the claim is that if you use them as the kernels, then you get exactly what you want. So if you use the Jth one out of here, you get a functional that has double zeros everywhere except for at the location 2j, where it has a simple zero with a positive slope. Okay, so omega j has double zeros at is equal to k for all k not equal to j, and a simple zero at s equal to j. So in other words, omega 1 has the right structure of double zeros to be the optimal extremal functional for the spectral gap maximization. And this omega j gives you the complete set of these b-type interpolation functionals that are like the first magic function, but they have a simple zero not at the first zero and not at the first vector, but at the jth one. So that's this is somehow the main result of my paper. You can construct these functionals. And then what we realized a few years later is that because of this mapping with the modular lambda, you can use the same functional, but instead of applying it to the two f1s, you apply it to the Gaussians. And what you get is exactly this Marina's beautiful contour integral representation for the Fourier odd extremal function for a-dimensional sphere packing. So, and more generally, if you apply the omega j, this omega j, from here, if you apply it to these Gaussians, then you get essentially get the b-type interpolation function. So just to convince a little bit more, this is the kind of contour integral that arises in our construction with the z variable, and if you map it to the tau plane using the modular lambda, you get exactly the kind of the four pieces of the contour integral that appeared in the sphere packing literature. So something that's interesting is that these integration kernels that we defined here, they're all quite simple. They're only rational functions and logarithm log of z minus 1. And so modular forms basically played no role for us. And the only way we get the modular form is using this single change of variables. So you get the modular form kernels from substitution z goes to lambda tau. So I didn't need to know almost any modular forms to find this magic function for here. All that you need to know is just translate it to the upper half plane from the z variable z plane. Something that's quite nice actually is that in the conformal bootstrap you can give also an explicit formula for the magic function. So this is when the functional acts on the two f1s, you can evaluate the integrals, and you get there's a sine squared, and the pole cancels the first double zero, makes it into a simple zero.
Gamma function and dilogarithm?
Yeah, it's a gamma function. There's some dilogarithm. So this is the magic function for the conformal bootstrap. Like if you take the same functional applied to Gaussians, you can no longer do the integral because it's an integral of a modular form times a Gaussian. But here you can evaluate it, and you can plot this, see the right structure of zeros. Then, well, for general P, actually, our story became much more similar to Marina's story. So what we did for general P is that we know the extremal spectrum, and then we figured out how to basically modify my contour integrals to be sufficiently general to accommodate the general P. So we basically have two integral kernels, which are subject to some functional equations. And these functional equations guarantee that there is some contour deformation in the z-plane that brings it to this form that exhibits this sine squared. Okay, and then we in this paper from 2018 with Miguel Palos, we asked what is the space of solutions for these kernels, and found kind of a basis for the space of solutions that this corresponds to this interpolation basis. So the space of solutions consists of these functionals that have double zeros pretty much everywhere except for one location. And one of them has a simple zero, and the other one is non-zero. Right? It nicely matches the basis for Fourier odd interpolation functions that were used in this paper to prove the universal optimality. So it all appears quite natural also in the conformal bootstrap. Yeah, so just to show you some more complicated formulas. Here's the kernel for general P. So the extremal functional looks like this. There is a sine squared integral over z with this. Oh, sorry, this should be h. I choose. This is the 2f1.
What does the tilde mean?
This should be h. Sorry, there should be no tilde. I changed notation when I was making the talk. So just imagine the 2f1 here, but this tilde is just a different normalization of the 3f2. Like there's some extra gamma factors. Okay, so this is the integral kernel for general P. For special case, what are they for the special cases for 8 and 24 dimensions? So they just become rational function. For general P, they're not rational functions, but for 1/2 and 3/2, they are very simple rational functions. And when you pull them to the upper half plane using the modular lambda, and you plug it, you basically change variables here. You get some kind of contour integral in the upper half plane, which is the precise. If you act on the Gaussians and sort of 2f1s, you get the magic function for 8 and 24 dimensions. Okay, so I think that's pretty much it. There have been some additional developments since that work. So something that I think may be quite interesting from sphere packing is this is a paper where we figured out how to kind of deform the construction, this contour integral construction that gives double zeros, but that moves them away from the arithmetic sequence. So this may be useful for some other dimensions where the Cohn+Elkies solution is not an arithmetic sequence. Then we also kind of use this interpolation basis functionals to learn some more detailed properties of the spectra. So this is just an upper bound on lambda 1 or S1. You can try to learn about the distribution if the gap between consecutive points in the spectrum can be arbitrarily large or not. So you can use these interpolation bases for that. But we didn't call them interpolation bases. And finally, the main problem that I was always interested in how to generalize it to higher dimensional conformal bootstrap, which is basically replacing SL2R by SON, 2. And that was more or less accomplished here and here. So here we figured out how to construct this unlock of the interpolation basis for this group. Well, that's what I wanted to say. So thanks very much.
Right. Very interesting. Are there other, I mean, this is a question to you and Marina and anybody else. Where do we understand or expect saturation in these linear programs? Do you have any kind of guess?
I think it's a mystery. There are just very few examples. Right here, there is all the examples that I think I'm aware of. The spectrum is very simple. So the spectrum is kind of an arithmetic sequence. I don't know. Well, I guess the two-dimensional.
From the point of view of conformal bootstrap or conformal field theory.
Yeah, these external functions, they don't really have a physical understanding. Like the way we found them was as a mathematical trick. So I don't think the physics really gives any new intuition for why they work.
It's not like these are exactly solvable cases or something like that. They don't relate.
Well, the extremal spectrum is this free fermion is an exactly solvable theory. So in that sense, it's an exactly solvable theory, but it wasn't guaranteed that this exactly solvable theory would saturate the bound.
Yeah, right.
That's still the hard part.
Yeah. Yeah. Any questions?
Yeah. Can you just say briefly how you mentioned that you had a free fermion correlation? How does that appear here, or is that just coincidental, or what?
Well, the nice thing about a free fermion is that it has a pretty large gap. It comes from the fact that you cannot put two fermions, you cannot put them on top of each other. That was the exclusion principle. So normally the ground state of two bosons would be when you put them on top of each other, and then the mass of this two-particle state is just twice the mass of the fermion as the gap of the boson. But when you have fermions, the gap is bigger because the fermions need to kind of be slightly away from each other and oscillate. And it turns out that in this case, it's the largest possible answer. So that's kind of the physical. Is that what you were looking for? Some physical?
More or less.
Marina wanted to say something.
Yes, but we can show a previous slide. So the rules that you have some spectral bounds. Well, first one, analytic extremal functionals with double zeros that do not form an arithmetic sequence.
Yes.
For which sets of double zeros does it work?
So it's let me see, it's only asymptotic, so it's not really, they're not exact double zeros. It is sort of in this asymptotic regime which corresponds to a large number of dimensions. This parameter becomes large, and then we can sort of modulate the location of the double zero in this, like in the double scaling limit, when the position of the double zero goes to infinity and also d goes to infinity. And we sort of give it a finite. It is away by a finite amount from where it's supposed to be. It's supposed to be at this arithmetic point, but arithmetic sequence, but we know how to put it a finite distance away. But if you wanted to understand the high dimensional strip packing, you would need to put them away by an amount which itself scales with. And that's something that we don't know how to do.
I mean, Marina, you said in your first lecture that in fact the Cohn+Elkies doesn't work in higher dimensions, or in some dimensions. I forget. 6 or something. You proved that it.
Yes, but that's okay. I mean, it doesn't work for sphere packing, but But here it might work for some other like reduced problems too.
Yeah, it could still, be that the asymptotics of Cohn+Elkies at large D is better than Kabaganski-Levenstein by an exponential amount.
But it's somehow there is this computational paper, and it seems like if there is an improvement, it should be like, I don't know. I think that they did computations like dimension 3000 or so, and it was not so clear. It seems like the victory over Kabaganski, theoretical victory over Kabaganski-Levenstein was still small, but That's clear. Maybe 3,000 is not such a big dimension. Or...
Oh, sounds like still like an interesting theoretical problem. What is the leading order asymptotics of the Cohn+Elkies problem?
And what with the SON2? What's the physical case? Is what n?
The most interesting is n equal to 3, but our construction works for n because the analog of the free fermion, which now actually becomes a free boson for higher D, it exists for n. So there's an optimal solution, and you can, well, in some cases you can find the magic function for this optimal solution for n.
All right. Well, it's a long day. Let's thank Dalimil for a great talk.